Welcome everyone. In this video, we are going to start our first project. It is a very simple project and all we need to do is to just print the blocks and threads IDs. So let's start and see how it goes. From the start menu, we are going to start the Visual Studio. As we explained previously, I told you that we need to install the Visual Studio. And then once it opens, all you need to do is to come here and create a new project. Then from this part, you are going to choose the CUDA programming language because in the first start, it looks like this. So instead of reading all of these methods or these projects, all you need to do is to come here and choose CUDA. And from CUDA, you can click here and click Next. Then you need to name your project. So I'm going to name it like, for example, test underscore 00. Or let's start 001 and then click create. As you see, this is our first project and the kernel here is called kernel.cu and we have some codes here, but we do not need all of these codes. I'm going to remove all of them because I want you to start from the scratch. So let's remove all of this and choose only some few lines, which I'm already prepared here. Okay, so we have here around like 7 or 10 lines. Those lines are dedicated for adding or including some headers, but I don't want to focus on this now. And I suppose that you already have a background in the C programming language, as we said in the requirements for this course. Okay, so here in this application, we have two kernels, or one kernel and one function. The function that we have here is the main function. And as we know from our C programming background, that each C programming application must have a main function. And because our CUDA is based on the C programming language, then it must have the main function also. So this is the first function. Then we have something called a kernel. A kernel in CUDA is equal to a function in the C programming language. So whenever you hear the term kernel, it means a function that is going to be executed on the GPU, not the CPU. But when we hear a function term in this context, this means that this is going to be executed on the CPU, not the GPU. Anyway, we know that this is a kernel, not a function, because of this slug, the global slug here, okay? So it is easy for now, and it is quite similar to the declaration of a function or the definition of a function. We have the type of the kernel, the kernel name, and these two brackets, and we do not have any inputs to this function, and these two brackets here, and this is an empty kernel, and we are going to fill this kernel now. So this is what we have. Within the main function, we have two instructions. The last one is just returning a zero value because we define the main function type as integer, so we need to return an integer value, and this is known from our C programming background. And I know that I'm repeating this because I want you to be familiar with the repeated stuff in this course. And the first instruction within the main function is this one, and this is just a call for this kernel. If you remember, if we have a function, then we can call this function within the main function. So how we can call a function or a kernel? It is very easy. All you need to do is to just write the kernel name, as you see. And then we have these parameters here that we are going to discuss today and see how they affect the output of our application. And then we can send here some inputs to use them in our execution or in our computations within this kernel. But today we are not going to send any inputs. For example, in the next videos, we are going to add two vectors. So we need to send the vectors here, and then within the kernel, we are going to read these two vectors and add them. But for now, we do not need to send any inputs or any parameters or arguments. So for now, this is what we have. A kernel, the main function. This main function is going to call this kernel to be executed. And as we said, this is a kernel, which means it is going to be executed on the GPU, not the CPU. So our purpose today is to print. We need to print the blocks and the threads IDs or indices. It is very easy. All you need to do is to just use the printf function. Okay, so let's see how we do this. We need to start with a slash n, which means we are going to print on a new line. Then we are going to write the block ID is %d, because the block ID will be an integer number, and then we write the thread ID is %d, and then we need to put here the variables that contain the values of the block IDs and the thread IDs. We have two variables here, and they are a predefined variables. Okay, so all you need to do is to just write block, and from here you can see the different block predefined variables. We are not going to choose the first one for now. The first one is the total number of threads in the application. The second one provides the block IDs. For example, if we have 10 blocks in this application, it is going to print IDs from 0 to 9. So let's click here, and then let's just write .x, because in all CUDA applications, the CUDA numbers can be distributed across different dimensions. So we have 1 dimension, 2 dimension, and 3 dimensions. Okay, so we are starting with the only 1 dimension now, so we are going to print the x value, or the x dimension value. So this is for the block ID. We need to do the same for the thread ID. So thread, once you write thread, you can see the thread ID x here. All you need to do is to write this and then click thread ID x.x. Okay, so now we have our application. All we need to do is to build this application to make sure that we do not have any errors or something. So from here, from this menu, click on build, and then click on build solution. It is building now, compiling and building. And as we said, it is going to compile our application using the NVCC compiler, as you see here. But this is already going to be done using the Visual Studio itself. We are not going to write a command line to compile this application, because we are using the Windows operating system. Students who are using Linux, they have to, especially if it is a Linux distribution for servers, then you have to learn how to use the command lines of the NVCC. And this will be shown in the next video. So in this video, I'm going to compile using this button here, but I am going to make just a small video to show you how to compile using the NVCC command lines. Okay, so all students should watch this video, not the students that use Windows operating systems. Okay, so as we see here, our build process is successfully finished. There is no any failures, 0 failures, and 0 up to date, so everything is good. Then the next step is to run this application by clicking on this button. Good. As you see, we have the printf here. Just do not focus on these 2 lines. Focus on the output of our application. The block ID is 0 and the thread ID is 0. Why do we have only one output here, and why it is 0 and 0? Because in our application, we determined that we have 1 thread and 1 block. So these 2 parameters here, let me just make a comment here to explain them. So we write the kernel name, and then these configuration, and then here we write the grid size. Or let me make it easy for you. Let me write the number of blocks. This is the total number of blocks in our application. Then we write comma, and we write the number of threads, but I need you to pay attention here. This is the number of threads, not in the entire application, but this is per block. And then this is the two brackets and then the semicolon. This is how it looks like. So we have one block, as you see here, and one thread per block. So let's start increasing the number of threads. For example, let's say 4, and then build our project to make sure that we do not have any errors, and then run our application. Okay, it's clear now, right? So we have one block, and this is how it looks like. And in this block ID 0, we have 4 threads. They start from 0 to 3, as you see. Okay, so this is how it looks like. Let's increase this value to 32 and then run. If you click run, it is going to build and then run. Okay, as you see, the block ID didn't change. We have only one block, so the block ID will be 0. And then we have different threads within this block, and as you see, we have 32, starting from 0 to 31. Let's change this number to this number of blocks to 2 blocks, and then make this just like 8 or something, and then click here. Okay, as you see, look at this part and check their block ID. Okay, so the block ID here is 1, and then the block ID here is 0. You might wonder now why the block ID 1 is executed before block 0. This is not important for now, but the first SM that will receive its block, the first streaming multiprocessor will get executed, and then it will be scheduled. It will be a scheduling between the printing values from one SM to another SM. But this doesn't matter now. All we need to know that we have 2 blocks. Their IDs will be 0 and 1, and within each block we have 8 threads, as you see, starting from 0 to 7. Okay, that is good, but let me try something else, something that is related to our reading of the white papers. In the Volta white paper video, I have mentioned, and I'm saying I have because this will continue throughout our course. Okay, I have mentioned many crucial points. One of these points is our GPU limitations. So let's try something and try to interpret this with our reading of the white papers. Let's say, for example, we are going to choose 512, which is power of 2. I am choosing 512, not 500 only, because usually we use power of 2 values in the number of threads. So in the number of threads within block, I'm choosing 512, and then let's run. Okay, it works fine. Just to focus here on the block ID, it is 0. But for the thread IDs, we have started from, it is actually showing here 96. But if you go down, you can see the 0 value. So it doesn't matter which ID is going to be printed first, but all of the IDs will be printed, okay? Because you are executing in parallel. We have, let's say that we have like 1000 cores. We do not know which one will finish first. So the first one finishes, it is going to print its value on the display or on the screen. So this is why it is not in order, because they all executing in parallel, and we do not know which one will be finished in at the beginning or first. So these are the total threads that we are determined in this application. Okay, now let's do something else. Let's increase this to double, 1024. Fortunately, it works fine. We have here the thread ID, the largest number of these IDs, which is 1023, and this is the 0 thread ID. So now let's increase Let's double this value again. Let's make it 2048 and then run. Oh, it doesn't work. This application didn't work as you see here. So there is no any output. And if you look at the building process, you can see that it is this application finished the compilation successfully, but it didn't work. Why? Because we have some limitations. Let me show you the white paper of the Ampere architecture, for example. Do you remember this table? I told you that we have maximum number of threads, maximum number of words, maximum number of blocks, maximum number of registers. So let's see what is the problem here. The maximum number of threads per, let's see, yeah, the maximum thread block size, this means the maximum threads per block, okay? So it is only 1024 in the Ampere architecture. This applies for many architectures actually, from the predecessors and also the next generation. So in this application, we cannot determine the number of threads per block to be more than 1024. Do you understand now why I was explaining the white paper in depth and focus on each particular table? This is why we need to understand both software and hardware. Okay, so let's go back to our application and try to find a solution for this problem. We have a problem now. Let's assume that I want to add two vectors in which each has like 2048 elements, okay? So what we are going to do, our application is not going to run if we choose here 2049. So you have many solutions here. One of these solutions, let's just put a comment here to remember that this is does not work, and try this and write 1024, but this is not enough for our vectors that have 2048 elements. So what we are going to do is to increase the number of blocks. Now the total number of threads in this application is equal to 2 multiplied by 1024, which is equal to the total number of elements in our application required in this application. Do you understand it now? So let's run and see if this application will run correctly without any problems. As you see, it works fine. Okay, so this is a problem and this is how you solve the problem. Now we can make this problem larger. Let's say that we are going to choose here like 2 million blocks. If that allowed in this GPU, you need to go to your white paper and see what how many blocks we can run on this GPU. So for example, let me see the maximum number of blocks, maximum thread blocks. As you see, thread blocks means blocks, okay? But I'm summarizing and say blocks, not thread blocks. So this is the maximum number of thread blocks per SM. We can have only 32. And we are writing here 2 million. So I want to ask you, can we write here a value more than 32? The answer is yes, because the 32 in the table is per SM, not per the entire GPU. So we need to know how many SMs in our GPU, and this comes from another table. Let's go up and see. By the way, I am not using the A100 GPU in this application, but I am taking this white paper as example, okay? So let's go up and see the other table. I can't remember where is it exactly, but we are going to find it. Yeah, this table. This table shows that we have like 180 SM in this GPU, which is not the GPU that I am using to run the application, but this is just an example. So we have 108 SMs, and the maximum number of blocks that we can run here is 32 per SM. So we can multiply 32 by 108. This is the maximum number of blocks that you can use in the application that runs on the GA100 chip or the A100 GPU. Do you understand now the relation between the software and the hardware? I want you to give me your feedback on these parts, because I'm going to make use of your feedback in enhancing the next videos. Okay, so I'm not going to increase the number of blocks too much here. I just want to show you the relation between the number of threads per block and the number of blocks, and how these numbers or parameters or inputs are related to the hardware limitations or the hardware resources.